Well, hello. As you've heard, I'm Stephen Taylor. Welcome to the Hooray Hall. My translation program tells me Hooray means idiot. So I know I am in the right place. Looking at you guys, I'm not quite so sure. I've been asked here to talk to you about functional programming and the array languages. Would you please put your hand in the air if you work or code with a language that supports array methods? For example, MapReduce. Yes, good. Now, keep your hands in the air. Keep your hand in the air if you work with an actual array language. APL, JK. Now look around. Look around. These are the languages that the array methods came from. And that's what I'm going to talk about today, and their relationship to functional programming. Functional programming, of course, starts with John Backus, who won the Turing Award in 1977. He didn't win it for his work on functional programming. He won it for his work on Fortran. But he gave a lecture and a paper for the award. The Turing Award, as you know, is pretty much the Nobel Prize for software. He gave a paper on Can Programming Be Liberated from the von Neumann Style? And that was the origins of functional programming, and he introduced FP, a functional programming language, which was influential, but nobody actually used. Functional programming, Wikipedia tells me, allows you to construct programs by pushing functions together, sort of like building blocks or a Lego game. And even Wikipedia notes it was heavily influenced by APL, developed by Kenneth E. Iverson in the early 1960s. That's the Ken Iverson that one of the three rooms up there is named after. And I want to congratulate the conference organizers on an excellent picture of Ken. It really captures the spirit of the man. So Backus got the Turing Award in 1977, and he recommended Ken Iverson for the award, which was given him the following year. So this is what I'm going to cover today. First, the secret history of the array languages. APL is older than COBOL. And in these days, it kind of survives as almost an esoteric tradition, like either Kabbalah or something, a secret society within the computer science community. I'm going to show you some of it, and perhaps the strangest code some of you will ever have seen. And I'm going to look at Tacit or Tacit expressions or point-free programming in APL to show you what it looks like. And my premise is that this is closest to what Backus had in mind with FP. You will judge for yourselves. Finally, in the fourth part, I will offer some reflections on the future. I'm the oldest guy in the room and an Australian, so I'm allowed to say things that nobody else can say without damaging their career. This part of the talk will cover some things some of you may find disturbs your precious and hard to maintain peace of mind. So you may wish to leave for that part, but if you find yourself upset by it, I'll be available to talk about these things afterwards, after the talk and after the conference. So, once upon a time, in Western Canada, right up there, not the bits you visit, some parts of Canada are spectacularly beautiful and mountainous. Not all of it. This is the Google Street Maps picture of Camrose, Alberta. And that's what it looked like in 1930, in the middle or the beginning of the Great Depression. The plains, after they'd been cleared of buffalo and Indians, were a very hard environment for the original settlers. The Scandinavians came there. Kenneth Eugene Iverson was born there in 1920. Iverson is a Norwegian name, anglicized from the original. This is Ken. The Scandinavians were used to tough environments. Here's some Norwegian settlers on the prairies. The house is made of sod, as they call it, cut out from the earth, because there's very few trees on the prairies and no stone to be had. And people would live through a prairie winter in a building like that, with the temperatures, well, I've been in Minneapolis when it was minus 40 degrees. Tough people. And taciturn. Tend not to talk, not to be chatty. So, Ken spent his childhood in the 1920s on the prairies. He was an adolescent in the 1930s during the Great Depression. He left school quite early, reasoning that the extra education was of no use to him unless he was going to go into teaching. But then in 1939, war broke out in Europe over here, and he joined the Canadian Armed Forces and served in the Air Force. And in the Air Force, if you had any mathematical aptitude, you were likely to wind up learning navigation. When the war ended, the Canadians had a version of the American GI Bill, and Ken got the opportunity to go to college for a university education. He did mathematics and physics at Queen's University, and Ken graduated top of his class in mathematics and physics. And from there, he went on to Harvard, and this is where our story gets really interesting for us. His supervisor was Howard Aiken, who built, or was on the design team for one of the very first electronic computers anywhere, the Harvard Mark I computer. It's probably got less computing power than my wristwatch, but there it is, filling up a large room. And Ken was assigned as the research assistant for Vasily Leontieff, an economist. Leontieff was working on his economic input-output matrices, which won him the Nobel Prize for economics. And Ken was his guy to do the math. Ken was appalled, in his own words, to find that there was no suitable notation for describing the computations through the tensor calculus. And coming from Norwegian stock on the prairies, he made his own tools. So this is an extract from a modern text on the input-output matrices. Ken's job was to make this into something that could be computed. And we can see here an early form of his notation, complete with little arrows for branches. This was useful enough that he got asked by Harvard to teach the world's first computer science course, though it wasn't called computer science in those days, but automatic data processing. He did that with Fred Brooks, who went on to a famous career of his own. Fred was his teaching assistant, and between them they wrote 2 textbooks for the course, Automatic Data Processing, and Ken's notation went into a separate book, which he called a programming language, but this was still pencil and paper stuff, you understand. And this is an extract from the original 1962 book. Ken had very strong views on style, and he cut everything down to say everything exactly correct and just once. Brooks later said about his work with Ken, For me personally, the biggest contribution to my life was that Ken taught me to write. And he wanted things very concise. When in doubt, leave it out. When you're finished, quit. This is still good advice for writers. When Ken applied for tenure at Harvard, they refused it, telling him that the problem was he'd only written just the one book, and it was quite a small book. So it was the book that got him the Turing Award later, but they couldn't see that then. So Ken quit Harvard and went to work at IBM. And here he is at IBM Research, big facility in Yorktown Heights in upstate New York, with the team that gathered around him to implement APL as an actual programming language on an actual computer. What did the notation look like at that point? Here's Iverson notation in 1964. It was used in the very first formal description of a computer operating system, the System 360, which was IBM's big new range of computers at the time. And for the very first time, you got a theoretical and a formal model of how the internal processes worked. If we take a slightly closer look at it, we can see we've got the branches here, simply arrows. We've got lines of the code are numbered, and we've got branches to particular numbers. But you can see in this, in the early 1960s, the beginnings of imperative programming. Let's pause a moment and look at the ancestry of the System 360. It had started off in the 18th century with Jacques de Vaucanson, the guy who made the famous mechanical duck, who'd put a design for a programmable loom for weaving. It didn't get built until Joseph-Marie Jacquard in 1805 actually put the thing together and made a mechanical loom controlled by punched cards. That inspired Charles Babbage with his analytical engine, and Hermann Hollerith, who made the tabulating machines with the legendary punched cards. Watson and the Computing and Tabulating Company in New York bought the American rights for that, and that became IBM, which originally worked with collating machines with punch cards, became the IBM 704 data processor, and eventually in 1964, the IBM System 360. I'm lingering on that a little because what all these machines are about are the stuff that you, as functional programmers, hate. State. State. The IBM System 360 is still basically a machine for managing state, and the programs for it are describing manipulations of state. This is my first computer, the Digicomp 1, also from about 1964. And I felt very cheated when I was given this. I was quite excited by it. I was going to get a computer, and then I found it had no flashing lights at all, just pieces of plastic. And eventually I grudgingly admitted that, okay, you could make it count down from 7 to 0. And if I'd been more thoughtful, I would have learned a great deal about it. But this is still basically a machine in which I'm manipulating state, and the ways of thinking about it are all state, state, state. The first If you go to Bletchley Park in England, where the work on decoding the German communications in the Second World War took place, you can see some of the earliest computing machinery there, and it's programmed with plug boards, things that you push into there. The first languages for manipulating these machines, like assembly language, are basically concerned with state. These are languages for engineers for moving things around. Better than pushing plugs in. And here's Fortran, back to John Backus from 1958. Still lots and lots of state, but this program is calculating the area of a triangle using the Heron's formula from ancient Egypt. We can see the beginnings of a relationship here. So while the computers are representations in the world of states, mathematics is about relationships and transformations. And we can see one here in Fortran, which is doing a simple calculation. Now let's move on from there to its equivalent in APL. So that funny stuff with the branch arrows eventually got linearized at IBM so that you could type it. The characters are a bit funny, but in those days the IBM Selectric typewriter would allow you to change the type head, so you could take off the little golf ball which had all the different characters on and replace it with one which had the APL characters, and you could type this stuff. So this here is the formula for the area of a triangle, and this is its representation in APL as of about 1966. And we get a thumbs up from the taciturn Norwegian because it's nice and short. In fact, we can see that the APL is actually shorter than the conventional mathematical notation. Oops. There we go. Now, this is way before your time, but I remember this. From the 1960s through till about the 1980s, before personal computers arrived, APL was one of the primary ways in which you could do what these days we would call personal computing. And much of it was the stuff that later got taken over by Excel, doing budgets and spreadsheets and managing reports and so forth. But unlike PCs, which were affordable, to use APL, you needed remote access to a mainframe. The service was relatively expensive, so IBM managers had it, and managers in some companies like Xerox had it. These days, we would, I guess, call it a cloud service. In the 1980s, a protege of Ken Iverson's, Arthur Whitney, got hired at Morgan Stanley to write a language, to find a way to handle the vast streams of data that were beginning to come from the financial trading exchanges. And he devised a stripped-down subset of APL, which he originally called A, which was very fast and which used its vector operations to process the feeds and to do calculations in ways that were fast enough to actually help the financial traders. That grew into the business KX, The language A became K, which is a blend of APL and Lisp. I think Arthur must have made somewhere between $30 and $50 million out of this work, which is quite a lot of money for a programming language designer. But for 30 years, KDB has remained the fastest time series database technology. It's now got useful competitors, but it's still the fastest. This is Ken Iverson and Arthur Whitney at the APL 91 conference in New York City. Arthur's dad, Ewan, died early, but he was a friend of Ken Iverson, so Arthur became a sort of protege of Ken Iverson. And they are respectively the devisers of APL and KDB, and they both came from the same part of Canada, in Alberta. So some key features of the APL programming language, which is still alive and kicking today. It is concise and very expressive syntax. You've got array and matrix manipulation built in very simply. Functional programming. This is the language that John Backus credited as inspiring him for functional programming. You've got a general mathematical focus, built-in functions and operators, higher order functions. Simplicity and elegance. I think I did another talk about 10 years ago in which I attempted to explain why I'm not a very good programmer. And I eventually worked out that I'm not really very interested in machines or algorithms or speed. I just love the poetry. So the simplicity and elegance is my thing. A dedicated user community, applications in finance, and a rather nice learning curve. I'm going to move on to show you some of what it's like to work in APL. It gets talked about as a tool of thought, taking its title from Ken Iverson's 1978 Turing Award paper, Notation as a Tool of Thought. Paul Graham once said that a programming language should be like a pencil. It's for thinking in and sketching with, not for engraving stuff in stone. And that's been APL's boast, that it's a tool for thinking in. So we come on now to take a look at some of what it's like to write APL expressions. And we'll come back to the formula for the area of a triangle. And I want to draw your attention to some features. First of all, we have an array literal notation, which the poet in me just loves for its simplicity. No semicolons, no commas, no brackets, nothing like that. Just write the damn numbers down. We have a conventional multiply sign. Is that so much to ask that the multiply sign that we used in school should still work? We have map reduce as a single character. If you want the product of a list of numbers, multiply reduce. If you want their sum, it's plus reduce. There's a primitive which gives you the larger of two numbers. We call it max. If you want the largest number in an array, you do a max reduce. Iteration is built into most of the primitives. So the business of writing loops and stuff, which I know you can do in your sleep, most of the time you just forget about it. Doesn't occupy your thoughts at all. In this example, S is a single number, ABC is a list of numbers. You can subtract a list of numbers from a single number. You don't have to explain how you want that done. For the mathematicians among us, A equals A plus 1 is always false. And mercifully, there's no operator hierarchy, so there's no need to remember which operators you apply first. A friend of mine likes to call this the republic of operators. Everybody's equal. In this example, the right argument of the multiplication is everything on the right. So what does that star mean? That's not a rhetorical question. Over to you. Again? Sorry, I couldn't hear that. Exponentiation. Thank you. Yes. Yes. It's quite readable. Now let's look at what point-free programming can look like in this language. Here's a list, a numeric list, and here's a function called tally, which gives you the length of the list. I mentioned that MapReduce is, or the reduce part of it is a single character, so there's the sum of x. And the sum of x divided by the tally of x is, of course, the statistical mean. We can write our functions in something like the lambda notation. APLers call them defins for direct definition, but they're the same thing. So you can recognize the code on the top line, and here we've simply named that expression AVG, average of x is, and applied it. Simple, simple. Here it is in the tacit form. We can see the sum, we can see the tally, and between them is the divide. Implicitly, the sum is applied to x, the tally is applied to x, and then the two things are divided. This is called a fork. And we can take the fork, the composition, assign a name to it, and apply it like that. Going over that again, here's the syntactical form of the fork. We call it a three-train. So f, g, h on x is f of x on g, f and x, h and x, and g between them. We sometimes talk about the side functions in a fork as the preprocessors. Preprocess the argument and then apply the binary function between them. Here's another three-train. Let's call that first one AVG, as we did, and introduce a new function, identity, the identity function, which simply returns its argument. So if we make a new fork, identity greater than AVG, we effectively get x is greater than the average of x. And we flag all the elements of x that are greater than the average. That's what I've got on the hat. If you want a hat like this, talk to me afterwards. So you can see the elements of how we compose the forks together. And here we've got three examples of the Tacit style, fairly simple ones. The average, above average, and this one which identifies all the elements which are not the mean, which my friend calls don't be mean. There are limits to Tacit. These are my thoughts on when not to use them. The virtues of Tacit. Any fans of the Jack Reacher novels? Yeah. Everything I need, nothing I don't. But code is a mapping from things in the real world. Here's some real triangles, which in the world of ancient Greece, which, as you know, all their triangles were blue. Here's some bytes, and the code is a mapping between these two. Sometimes you need the mapping to be explicit. So here we can see S is defined as the semi-perimeter of the area. We're calculating the area of the triangle. Here, this is the same thing as a one-line lambda. And now we no longer have the semi-perimeter identified. Maybe we didn't need it. We can just blast through that. And here it is as tacit. So tacit means silent, and it allows you to say nothing, to be taciturn about the parts of the mapping that you don't want to have in your head. But if you want the semi-perimeter in your head, if that's part of the way you think about it, then you probably want code like this, and Tacit is not for this application. A crafty little quote here from Ludwig Wittgenstein. Tacit stops you speaking about certain things. That might be to your advantage, but it might not be the right thing to you for the particular problem you're working on. Okay, lastly, I'm going to finish with some things we need to talk about as software developers. And this is the part which might disturb your peace of mind. So if you want to stand up and leave the room at this point, that's fine with me. Okay, no takers. When I was very young, this is what the future looked like. There was going to be flying cars, space travel, and with automation and artificial intelligence and robots, abundant leisure. It's not what that same future looked like now. We're facing multiple harvest failures. We already have wildfires, heat waves, flooding, rising sea level, wars, mass migrations already starting, and scholars are warning about the prospect of social collapse. So, question is, what does that mean for us as software developers? First question here is, what's it like when a civilization collapses? Because this isn't the first time it's happened. And it collapses the same way a business fails, first slowly and then very quickly. What we can expect in our work is a general decline in reliable infrastructure. We've already seen the start of this, everything from potholes in the road to power outages, supply chains that are starting to break down, and we can also expect rising energy costs. So a strategy for software development in this scenario is to stay close to your customer and avoid dependencies on complex infrastructure. Stina, my colleague from Dialogue, was going to talk more about this aspect of APL this afternoon. Unfortunately, she's not. So in a nutshell, my predecessor as editor of the Vector Journal was once asked, what does APL still have to teach computer science? And he said, nothing. All the good ideas, MapReduce, the REPL, and many others have already been adopted, noted, and you can find them elsewhere. But if you wanted a language in which to make $1 million from building and selling software, APL is your guy. So we're not going to try and expand on that. You can talk to me afterwards. That was what Stina was going to talk about this afternoon. There are plenty of examples of people who've started with some mathematical tools for their own use and built them into big businesses. A tip, watch K and KDB at shakti.com for very fast, low-energy vector ops, the possibilities of training LLMs locally with low energy costs. They're talking several orders of magnitude improvements in energy consumption or calculations. And lastly, good luck. I'm way older than most of you, so I'll be out of this long before you are. You can find me at lambentechnology.com. We can talk about the changes in the climate and all the implications at alreadyhere.uk. Thank you for your attention.